Hello everyone. For those who don't know, my name is Jalen, and I'll be taking care of you guys and showing you what IR spectroscopy is about. So, on today's agenda, I'm going to go ahead and tell you guys a little intro on to spectroscopy. Then we'll go into IR spectroscopy. Then we'll go ahead and talk about signal characteristics. And then we'll go ahead and do some example problems. So, I'm going to go ahead and go over spectroscopy. So to kind of start off right, spectroscopy is the interaction between matter and electromagnetic radiation, or otherwise known as light. And light contains both wave-like and particle-like properties, allowing it to be viewed as both a wave and a particle. If you view light as a wave, it has perpendicular oscillating magnetic and electric fields, and there are two main characteristics in waves. There are both wavelength and frequency. For those who don't know, the wavelength is the distance between two adjacent peaks, like from crest to crest or from trough to trough. Frequency is the number of wavelengths that pass a particular point in space per unit of time. And the one thing I want you guys to remember is that frequency is inversely proportional to the wavelength. So one example could be if the wavelength of a wave increases, then the frequency decreases. If you see light as a particle, it's called a photon, which can be thought as packets of energy. And the one thing I want you to take away from this is energy is directly proportional to the frequency. Okay? So we know that light contains many different types of radiation, and scientists were able to collect them and put them into a chart called the electromagnetic spectrum. And the reason why I add this here is to kind of show you guys some of the radiation that we've used in some of the chemistry classes you may have taken. For example, if you took Chem 1A, you did a food dye lab where you analyzed the absorbances of red and blue food coloring, and you utilized a piece of equipment called a spectrophotometer, which uses UV and visible light to help you measure those absorbances. If you're in L-Chem, particularly in Chem 12B, you're going to utilize a piece of equipment called the NMR machine, which uses radio waves to help you determine the arrangements of hydrogen and carbon atoms. And for a lot of chemical analysis, we use a piece of equipment called IR spectrometer, which uses IR radiation to help us determine the functional groups within a sample that we're looking at. So remember, in spectroscopy, the nature of matter is heavily involved in how molecules rotate. And the one thing I want you guys to remember is energy is quantized. And you may be wondering, what does it mean for energy to be quantized, right? And to kind of put simply, it basically means that energy is restricted to certain levels by nature, right? For example, in front of us we have an energy diagram, and you can see we have these horizontal lines, right? Those represents different vibrational energy levels, and bonds are can only vibrate at those levels, right? If a bond has an energy that is between the energy levels or the horizontal lines, it's not going to be able to vibrate. It can only vibrate at the energy levels that are signified by the horizontal lines, and the gaps between each of the lines is called the change in energy, or you may see it as delta E. And like I said before, right, if a bond possesses energy at these specific levels, it can absorb a photon of the same energy, which will promote a vibrational excitation, which is stored in the bond, and then it will be slowly released as heat. So that's pretty much it for spectroscopy. We can go ahead and talk about and go more in depth into IR spectroscopy. So remember, there are two main types of vibrations. We have stretching and we have bending. V1 and V3 are examples of stretching vibrations. V2 represents bending vibrations. X, Y, and Z represents rotational vibrations. And solely for IR spectroscopy, we mainly look at stretching and bending, so you don't have to worry about the rotational vibrations for now. So in chemical analysis, many chemists primarily use IR spectroscopy because each bond absorbs different amounts of energy. Right? For example, a CH bond will absorb more energy compared to a CO bond. Right? And this is because each type of bond will absorb a characteristic frequency, which allows us to determine that type of bond within a compound. Right? For example, if I'm analyzing alcohol, right, alcohols have an OH bond. That OH bond will only absorb a frequency of I radiation that has the same amount of energy as an OH, an I radiation, right? An OH bond is not going to absorb a photon that has the same amount of energy as a CH bond. Right? It's not going to do that. So in the lab, right, we'll be using, like I said before, we're going to use a piece of equipment called a FT-IR spectrometer to help us determine the functional groups within our synthesized MOF199. So right in front of us, these are the two IR spectrometers that you'll be using to help you analyze the compound. For those who don't know, FT-IR stands for Fourier Transform Infrared, and how you can use these equipment, right? So when you synthesize your product, you're gonna go ahead and put your sample onto this metal circular plates that are on the spectrometers, and from there, the spectrometers will shoot a beam of radiation into the sample. What's gonna happen is some of the radiation will pass through the sample, and some of the radiation will be absorbed. The machine is going to use a mathematical operation called a Fourier transform to determine which radiations passed through the sample and which ones didn't. And from there, it's going to go ahead and create a graph that will display the frequencies that did not pass through the sample, and those are the function groups within the compound. So this is an example of a graph a spectrometer could produce, and the proper terminology for this is called a absorption spectrum. You may hear me call it an IR spectrum. That's what I've called it when I was taking OChem, and you can either refer this to a absorption spectrum or an IR spectrum. It doesn't really matter. So basically what the graph is composed of, on the y-axis, that represents the percent transmittance, which displays the strength of each of the signals. In the x-axis, that represents the wave number, and it shows the location of the signals. And each of these broad and sharp peaks, those are called the signals, and those are the function groups that are within the compound. And the way you read these signals, anything to the very far left of the graphs is called the diagnostic region. And typically those contain the more important signals, and those would tell you the functional groups of that's within the compound. Anything to the far right, relatively, I guess, around anything below 1500, that represents the fingerprint region, and typically those regions are pretty messy and really hard to analyze. I guess one cool thing about them is in the fingerprint region, those display unique patterns to only one compound. Right? So if you're analyzing both of these compounds, on the left we have 2-butanol, on the right we have 2-propanol. Well, they both have this similar peaks in the left side of the graph. On the right, they both display different signals, which are only unique to them only. It's kind of like us humans, right? Each one of us have a different unique fingerprint pattern, and in chemical compounds they have a very similar thing, and those are visualized as these peaks that you see on the right side of the graphs. Okay, so we're going to move on to signal characteristics, and the first one that we're going to talk about is the wave number. So, wave numbers are dependent on both the bond strength and the masses of the atoms. And this can be visualized if we treat a bond with a spring that's connected to two weights as seen in the top right hand corner. This allows us to construct an equation that is derived from a physics concept called Hooke's law, which can help approximate the frequency of a bond between two atoms. And so in the equation, you can see that we have the variable f that represents the force constant, or known as the bond strength. In the denominator of that same fraction, you have m rep, which represents the reduced mass of the system. And you see that since the reduced mass is in the denominator, If that value is small, it's going to go ahead and produce a high frequency, and due to a higher frequency, the peak will appear at a higher wave number, right? And a similar thing can be seen with the bond strength, right? Remember, each bond will have a different force constant, and if a strong bond is present, and for our case, let's say we had a triple bond, right? It will vibrate at a higher frequency, and it will allow its peak to appear at a higher wave number. So, after many experimentation and analysis, scientists were able to determine where each of the bonds are located. For example, anything below 1500, you have your single bonds. If you're between 1600 and 1725, those are where your double bonds will be. Anything between 2100 and 2300, those are your triple bonds. And anything that bonds to a hydrogen, for example, a CH bond, an OH bond, or an NH bond, right? Those will appear between 2700 and 4000. So there are two things that affect the wave number, and the first one we're going to talk about is the hybridization states. If you're currently taking Chem 1B, you'll learn this more towards the end of the semester. But for those who haven't, remember that. For those who have already taken Chem 1A, right? Remember that carbons can be either sp hybridized, sp2 hybridized, or sp3 hybridized, right? If a carbon is sp hybridized, its orbital will have more s character because its electron density is held closest to the nucleus, kind of like an s orbital, right? As you can see at the bottom. As a result of this, the bond will be much shorter than a sp2 carbon or an sp3 carbon, but it will be the strongest. And since you have a strong bond, it will have a higher frequency, or it will vibrate at a higher frequency, and its wave number will appear, it will have a larger wave number. So you can see it in the top image. If you have sp hybridized carbons, those are your alkynes, and it will have an additional peak at roughly 3300. If you have sp2 carbons, they will also have an additional peak, but it will appear roughly around 3100. And alkanes, which are sp3 hybridized, they won't have that additional peak because remember, single bonds are the weakest and it won't appear within that region. Okay. The one thing I want you guys to remember is if you're analyzing a compound where you know it has a double bond or a triple bond and those additional peaks doesn't appear, that doesn't mean that the compound does not have a double bond or a triple bond. And there's two cases where this is true. On the left, you have a tetrasubstituted alkene, and on the right, you have an internal alkenes. And you can see that the sp2 carbons and the sp carbons do not bond to a hydrogen. So what's going to happen is when you put those in an IR spectrometer, you won't see those signals. And it's because, remember, between 2700 and 4000, the spectrometers will analyze carbon-hydrogen bonds. But since those carbons aren't bound to hydrogen, those peaks won't appear. So you do want to be careful when you're analyzing those type of compounds. If you don't see those additional peaks, just remember that you might still have a double bond or triple bond. Okay? The second thing that affects the wave number is the resonance. To kind of help me demonstrate this, we're going to go ahead and look at a ketone, which is on the left, and a conjugate ketone, which is on the right. For those who don't know, a conjugate ketone is a compound that has two double bonds that are separated by one single bond. So for the ketone, right, it has two resin structures, and looking at the two resin structures, the ketone has some double bond character, as seen in the left structure, and it has some single bond character, as seen in the right structure. And to kind of help determine the nature of the bond within the resonance hybrid, we need to analyze what each stranded structure offers. We can see that in the second structure, that contains a charge separation, as seen by the negative and positive sign, and a carbocation. For those who don't know, a carbocation is a positively charged carbon atom. And for those reasons, the resin structure will only contribute a small amount to the overall hybrid, and for that, the ketone will be composed of mostly double bond character. For the conjugated ketone, right, there's 3 resin structures. Just like the ketone, the second structure looks a lot like the second structure for the ketone. You have a charge separation and a couple cation, and for those reasons, it's not going to offer a lot to the overall hybrid. But the third one will. The third one has the charge separation, but that structure has more S character, or sorry, single bond character, right? Since it has more single bond character, their overall hybrid will therefore have more single bond character. And the effect of this, right, in the ketone, the carbonyl peak has more double bond character. Remember, double bonds are a lot stronger than single bonds, so its carbonyl peak will appear roughly around 1720 in the IR spectrum. While the conjugated ketone, since that has more single bond character, its carbonyl peak will appear roughly around 1680. So that's it for the wave number. I'm going to go ahead and talk about the intensity of the signals. So when you look at an IR spectrum, right, some signals may appear stronger than others. I guess for a visual idea, strong bonds will have a longer peak, while weak signals will have a shorter peak. You kind of see it in the top left-hand corner. And this is because some bonds are more efficient at absorbing IR radiation. So in chemistry, right, the one thing that you want to remember is atoms have partial charges, right? So when a bond vibrates, the distance between the 2 partially charged atoms will change, and because of that, the strength of the partial charges will also change. And the strength of the partial charges is defined as dipole moment, which is essentially an oscillating electric field that surrounds the bond, which is used as antenna to absorb IR radiation. And since both the IR radiation and the dipole moment are both oscillating electric fields, they both can't interact with each other. The efficiency of how a bond is at absorbing IR radiation is determined by the strength of the dipole moment. Right? Just looking at the top right-hand image, we're going to go ahead and look at a carbonyl, which is a carbon double bond oxygen, to a regular double bond, carbon double bond carbon. Right? Remember that oxygen is one of the most electronegative atoms, and because of that, it will have a very large partial negative charge. And the carbon that the oxygen is bonded to will therefore have a very large partial positive charge. And when the bond is vibrating, as the oxygen and the carbon bonds come close together, it will have a very large dipole moment because you have very large partial charges. In the regular double bond, both carbons will have some partial negative and positive charge, but it's not as strong as the oxygen in the carbonyl and the carbon in the carbonyl. Right? Because of that, the carbonyl group will have a much stronger peak compared to the regular double bond. Right? So when you analyze in the graph, you can see that the very high peak in the carbonyl group, that's when the atoms are close together. You can see that this is much stronger compared to the regular double bond. Okay. The last thing we're going to talk about is the shape of the signals. So in an IR spectrum, there are typically only 2 shapes you'll see. You'll see a narrow signal and a broad signal. And the only time you'll see a broad signal is when you're analyzing an alcohol. And remember that alcohols have an OH bond. And basically, when you have an OH bond, that alcohol group can do hydrogen bonding. For those who don't know, hydrogen bonding is one of the 3 intermolecular forces compounds can do. And one effect of hydrogen bonding is it can weaken the existing OH bond. So basically what this means is that in a sample, right, you will have some compounds or some alcohols where the OH groups will do hydrogen bonding, while you will have other alcohols whose OH bonds will do hydrogen bonding. And because there's an inconsistency of OH groups that do and do not do hydrogen bonding, it will weaken the signal and making it broad. In some cases, you'll see an alcohol peak that will appear narrow, and the only time you'll see this is if you dilute an alcohol in a solvent where the OH groups can't do hydrogen bonding. In some cases, you'll see 2 alcohol peaks, one narrow and one broad, in the same spectrum. And to achieve this, you will dilute an alcohol in a solvent where the solution is neither concentrated nor diluted. And the reason why you'll see the two signals because some of the OH bonds will do hydrogen bonding, while other OH bonds don't. So an example of all these characteristics, they're typically seen in carboxylic acids, right? So on the very right, we have a IR spectrum of ethanolic acid, or its function group is a carboxylic acid. You can see that in the very left side of the graph, you have that very broad peak, and that comes from alcohol groups. You can see that it is so broad to the point where it's going to overlap with the CH peak, which is right here. This is because carboxylic acids are able to form dimers through hydrogen bonding. And for those who don't know, a dimer is a molecule that is formed by using two identical units that are connected using hydrogen bonding. An image to help you visualize that is seen on the top left-hand corner. You have two ethanoic acid compounds, and the dashed lines is hydrogen bonding, and that will help you form a dimer. Okay, so that's pretty much it. Let's go ahead and go over some practice problems that kind of help you guys analyze our spectrums. If you haven't pulled it up yet, I recommend pulling up Professor Donna's IR correlation table, and that will help you analyze the spectrums. Okay. So, as a kind of review, right, in my first video, I talked about the functional groups, and what I want you guys to do right now is pause the video and take some time to analyze this compound and determine the functional groups are represented in this compound, right? So go ahead and pause, and when you're ready, unpause, and let's see if you got any of them correct. Okay, so let's go ahead and show you guys the answers. So all of these are the most common functional groups that you'll see in organic chemistry, right? And I highly recommend that you do your best to memorize them, because we might see some of these examples in the MOF 199 when we analyze our synthesized product using the IR spectrometers. Okay, so our first example of an IR spectrum is, I want you guys to go ahead, pause the video, and determine which kind of function groups is represented in this IR spectrum. And once again, I highly recommend that you use the correlation table to help you do so. Okay, so let's go ahead and break it down. So typically when we're analyzing an IR spectrum, we want to go ahead and just immediately focus on the left-hand side of the graph, because that's what's really important. Those signals are the signals that we want to analyze to determine the function groups within the compound. Remember, anything on the very far right is the the fingerprint region. Those are pretty messy. We don't want to analyze those. But anything on the left side, we do want to analyze those. Okay. So that very narrow peak that we see right here, this is roughly around 2980 to 2850, right? Typically these are your CH bonds, and looking at the R quotient at the very top, those are for alkane CH bonds, which are for sp3 carbons. Looking at the options, right, you have an OH bond, a carbonyl bond, an NH bond, and a carbon sp high-res carbon, right? For an sp high-res carbon, we need to see an additional peak roughly around 3000. Right here, we don't really see that bond 3000, so we know that we don't have an alkyne, an alkyne, so we can eliminate carbon D. But looking at this region here, we see a very broad peak, right? If you remember from the things I talked about not too long ago, alcohols are the compounds that only have a broad peak. And if you remember, alcohols are composed of OH bonds, so therefore A will be the option here. For this example, you see two alcohol peaks. You have this narrow peak here, and this broad peak here. And this is probably because the alcohol is dissolved in the solvent, where the solution is neither concentrated nor diluted. Remember, for this example, some of the OH bonds in alcohol is doing hydrogen bonding, and some aren't, and that's how we are able to see these two peaks here. I guess one kind of thing to kind of take away is if you see any broad peaks, roughly around 34 or 3500, those are typically alcohol peaks, and those are, depending how they're orientated, you can either have just a regular alcohol or a carboxylic acid, right? If you have a carboxylic acid, this alcohol peak has to be merging with the CH peak here. Going to the next one, go ahead and do the same thing, pause the video, analyze this hour spectrum, and determine which of the following options is seen in this hour spectrum here. Okay, so once again, we're mainly going to be looking at the left side of the IR spectrum. Probably should have mentioned in the last one. Typically, you always want to analyze anything past 1500. Those are your more important signals, right? Anything below 1500, don't look at. But anything above 1500, do look at. As seen over here, you have your standard CH peak. This is for your alkynes. And I guess one cool thing is every compound will have this peak. It's roughly around 2980 to 2850. And you can see the option here. We don't have an example. We don't have an option of the regular alkane. What do you call it? The alkane peak, or which is sp3 hybridized. Option D, that's only an sp2 hybridized carbon. That peak will appear around 3300, and we don't see that additional peak, so we can eliminate carbon D. Your alcohol peaks, right? Those are broad, right? This little peak here, this will really be considered as the peak that you will look at, and it's not broad, so you can go ahead and eliminate that as well. So you're left with option B and option C. Looking at option C, those are typically an amine, right? And looking at the ion correlation table, amines, if you have a primary amine, you'll see two peaks around 3500, and these are form of a doublet. If you see a secondary amine, you'll see a peak around the same area, 3500. You don't see that here, so you can eliminate option C, and by press elimination, our answer is B. Look at the very end. If you don't want to use press elimination, look at the hour correlation table at the very bottom. You have a category where you have C double bond O's. Those are all the carbon yield peaks that are in like aldehydes, carboxylic acids, anhydrides, esters, ketones, right? Those typically appear around 1700. We have this very strong peak here, which is roughly around 1700, and that's evident where this R spectrum has a ketone or a carbon yield group within the compound. And a lot of people ask in the in-person meeting, oh, we have these functional groups like a carboxylic acid, ketone, anhydrides, esters, aldehydes, where they all have a carbon yield peak. How would I know which function group is being displayed in this IR spectrum? And I guess the answer is you can't. IR spectrums tell you the functional group that is within a compound and determine whether it's like an ester, carboxylic acid, ketones, or one of any of those functional groups that do have a carbon yield group in it. You're going to have to rely on other spectroscopy techniques like NMR spectroscopy or mass spectroscopy to help you determine those. Right? So going to move on to the next question. Again, the option is B. Okay. So this is going to be a little bit more tricky now. Before we're determining the functional groups. Now I want you to go ahead and determine the compound within this R spectrum. Like before, go ahead and pause. Use your calculation to help you figure it out. And when you're ready to see what the answer is, go ahead and unpause the video. Okay. So remember once again, when we're analyzing the R spectrums, we want to analyze anything past 1500. Okay. Starting with the first peak right here, this is a carbon yield peak, which is roughly around 1700. If you look at the very bottom of the IR quotient table. That really isn't helpful because all of these guys here have a carbonyl group in it, so that won't be useful. Look at this very big thing, right? We can see that if we split this peak in half, on the left side we have a broad section, on the right side we have a very rigid section. And this is a characteristic of a carboxylic acid, right? Only carboxylic acids have these IR peaks. To look at our options, we can go ahead and eliminate D, because that isn't a carboxylic acid, that is a aldehyde. We can also eliminate B as well, because this functional group here, that is an ester. Right? We can also eliminate that. So we're left with A, and we're left with C. Okay? We can see that the difference between A and C is that A has an alkyne. Remember, alkynes, they're going to have an additional peak around 3,000, okay? You can see that this section here ends at roughly around 2980. If you look around anything past 3,000, we don't see an additional peak anywhere on this broad section, right? And since we don't see any signals past 3,000 aside from this broad peak, we have there's no alkyne present, there's no triple bond present. So we can eliminate A, now we'll leave our answer to only be C. Okay? There we go, right here. Move on to the next question. Okay, same thing. Look at the IR spectrum and determine which of the following compounds is represented by this spectrum. Alright, once again, analyze anything past 1500. This very long peak here, this is an example of a carbonyl group. Looking at all of our options, they all have a carbonyl group, so this piece of information isn't that important. Over here around 3000, we have a lot of peaks that we can analyze. This middle one here, this is an example of a CH peak, an alkyne CH. All the compounds, or typically every organic compound, will have that information, which isn't very useful. Looking over here, we have an additional peak, roughly around 3100 to 3200. And if you remember, alkenes have this example, or have this peak. If this is roughly around, what is it, 3100, right? This is what, 35. So it can either be an alkyne or an alkene. Looking at our options here, the only compound that has an alkene in it or a double bond is option D. And just solely off of this peak here, you know that our answer can only be D, because everything else does not have a carbon, double bond carbon. Right. And the one thing, and if you want to end it there, that's fine, you have the answer. But there's one more piece of information that will also help you figure out which of the full option is represented by this IR spectrum, and that's from this one here. So looking at the very top in the CH section, right, you have a spot where it says aldehydes. Aldehydes have a doublet roughly around 2850 or so. We see this doublet here, and this peak is representative of an aldehyde. Out of all the options, the only one that has an aldehyde is option D, as seen here, and that's another piece of information that can help you determine the functional group, or help you determine the compound from the IR spectrum. Okay, and that's all the example problems. And if you're still wondering what is the importance of IR spectroscopy for our lab, well, there's option D, there's option here. So on the left, this is the IR spectra of fresh MOF 199, as seen in blue, and you have reused MOF 199. And during the lab, after we make a product and all that, we analyze in the IR spectrum. If we get either A or B, that's because we have MOF 199 in this pumpkin. This is gonna be us after we find out that we successfully synthesized MOF 199. If you don't see it, that's fine. You know, that's the fun part of chemistry and lab work. But if we do get any of these graphs here, this is gonna be us at the lab. Okay, that's pretty much it. In the email I sent out, I believe on Wednesday, there's additional practice problems. I recommend you guys practicing those, get comfortable using the iris correlation table, get comfortable analyzing iris spectras. If you ever need help, feel free to let me, Eamon, Crystal, and Ian, we'll be glad to help you guys out and answer any of the questions that you guys have. Okay. But other than that, thank you for watching and best of luck.